to a start. I'm going to go ahead and start the Pear Deck class. If you have not yet joined, the instructions you can find for joining are going to be in the chat. First of all, my name is Paul Furman. I teach physics at Thompson High School in Alabaster. I'm joined by Ms. Demler, who teaches at Hewitt-Trussville High School. There she is waving. So I've been teaching AP Physics. This is my 9th year, and I've been doing these sessions for A+ College Ready for probably 7 or 8 years now. We're going to be doing a session on kinematics tonight. Kinematics is typically the first unit that you'll encounter in AP Physics 1. We will be using Pear Deck periodically. There will be a question that will be posed on screen. Might be one where you have to write a little bit with your mouse or your stylus or your finger, or it may be a multiple choice that you can enter. And that just gives me an idea of where everybody stands and the types of misconceptions that you might fall prey to on some of these kinematics type questions. We have a relatively small group. Looks like we have about 6 students or so. If you have a question, don't hesitate to unmute yourself and ask a question, or if you're more comfortable posting it in the chat, Ms. Demler will monitor the chat, and if you have a question, chances are good that somebody else has it, and it's not an imposition to ask, because the whole purpose of this session is to help clarify and reinforce some of the kinematics topics that you may encounter. So I will continue. The first opportunity for you to provide some input is just to indicate, where are you with kinematics? Have you never heard of it? That would be answer A. You understand the basic definitions, but maybe need a little more help. B, or this is something that you understand completely and you could teach this session yourself, would be the third option. And looks like we have mostly B's, but a couple of C's. So that's good. Hopefully it is something that you've already studied and completed the unit, but maybe it's just a little bit rusty, especially if you took it back in the August-September timeframe for last year. So basically, kinematics in a nutshell is the physics of motion, things that are moving from left to right, up or down. We're interested in several aspects of the motion: the velocity with which something is moving, as well as the change in position and the acceleration of an object. We'll talk a little bit about the difference between vectors and scalars. For example, velocity is a vector. It has magnitude and direction. Speed is a scalar. Speed just has magnitude. It has a number, but we don't talk about speed in terms of the direction of the motion. With velocity, we absolutely do care about the direction of the motion. You may see a question at some point that talks about the difference between distance, which is a scalar quantity, and displacement, which is a vector. And the way I generally describe the difference between distance and displacement is, if I travel 3 meters forward and then 1 meter back, I traveled a total distance of 4 meters, but my displacement would only be 2. Displacement is how far am I from where I started. So if I travel 3 meters forward and 3 meters back, I traveled a total distance of 6 meters. My displacement is 0 because I'm right back where I started. Mostly we're dealing with the vector quantities, but occasionally you'll see a question that checks to see if you understand the difference between the scalar and the vector. Position, variable for position is X. Position is arbitrary. My position could be 0, it could be 50, it could be 100 meters. Your position doesn't really matter so much as your displacement. So your displacement is your final position minus your initial position, also known as delta X. So in all the kinematic formulas, you'll see delta x. That refers to the displacement. And you can see that that second bullet from the bottom is x minus x naught. That's the final position minus the initial position. So mostly, 95% of the time we're dealing with displacement. Distance, I never use delta S. You just simply won't see it. Velocity is also a vector, and velocity is nothing more than your displacement, delta X, divided by your time. So velocity is measured in meters per second, and velocity is a vector. It can be positive or negative. Typically, positive is going to be if something is moving to the right or moving up. Negative is going to be just the opposite. A negative velocity is something moving to the left or down, although you will see problems where you get to define what the positive direction is. As I mentioned before, velocity is a vector, speed is a scalar. The next couple of slides that we're going to see give you an opportunity to interpret some motion diagrams. And basically a motion diagram, here's a set of 6 of them. You can think of this as the dot is an object. Maybe it's a ball that's moving, and imagine that it's completely dark except there's a strobe light that's flashing. And so every time that strobe light flashes, you see where the dot is. Strobe light turns off, the dot moves, some distance. Strobe light comes on, you see where it is again. So that's what each of these represents. So the question here, and this is your first opportunity to use Pear Deck, is to circle the motion diagrams which depict objects moving at a constant velocity. So if it helps, you can think of the strobe light gives you a point in time every second where that object is 1 second after the previous. And let's see, I see someone chose A, B, and D, A, B, and D. Someone chose A, B, skipped D. D is actually constant velocity as well. Notice that for D, the every 3, and we can assume this could be 3 centimeters, 3 meters, a distance of 3, but your dots are on 3, 6, 9, and so on and so forth. So D is a constant velocity as well. The next slide, same diagrams, but now you need to circle the diagrams that have a positive acceleration. So all of these objects are moving to the right. Which ones have a positive acceleration? And the answer on this one is actually C. The object is moving to the right, and so it has a positive velocity. And notice in C, every time interval, it's moving a little bit further than it did the previous time interval. So that would be a positive velocity and a positive acceleration. That would be an object that is speeding up. And the last one here is circle the diagrams that have a negative acceleration during any part of the interval. And looks like most of you are getting the last 2, E and F. That is very good. That is a true statement. So notice that with E and F, every time interval that passes, the object is traveling a little bit less distance than it did the previous time. So it's slowing down for every time interval. Don't want to spend too much more time on these. This is not something that I see real commonly on the AP exam. Well, not that I see the AP exam, but it's just not a overly common technique for representing motion. More likely, you're going to get a velocity time graph, a position time graph, or something of that sort. First multiple choice question here asks you to describe the velocity and the acceleration of this object. So note that the object is moving to the left, and it looks like the dots are getting closer together as it moves. And so that should tell you something about the acceleration. I have a few C's. Most of you have answered D. D is a common answer. The correct answer on this one is actually C. And it might seem counterintuitive that, wait, how can it have a positive acceleration? And when it comes to velocity and acceleration, you can have every possible combination: positive velocity, positive acceleration, negative velocity, negative acceleration, or you can have a positive and a negative mixture: positive velocity, negative acceleration, or negative velocity, positive acceleration. Here's the rule of thumb. Once you learn it, it's very, very easy to apply. If an object has the same sign for velocity and acceleration, it's speeding up. So if I have a positive velocity and a positive acceleration, I'm speeding up in the positive direction. If I have a negative velocity and a negative acceleration, the easiest example here is if I'm standing on top of a building and I drop a rock, that rock starts traveling down. That's negative velocity and it's speeding up. And we know that that negative velocity is going to be negative 10 meters per second squared because it's accelerating due to gravity. So if the signs are the same, velocity and acceleration, it is speeding up. If it's slowing down, the signs are opposite. Or if the signs of velocity and acceleration are opposite, it's slowing down. So I think probably everybody pretty easy to get the velocity direction. The velocity is negative. And if you look at the dots, it's slowing down. And so if it's slowing down and you have a negative velocity, the only possibility is for the acceleration to be positive. So it's a little bit counterintuitive that something could have a positive acceleration and be slowing down, but it's very easy to see once we get to motion graphs, which we'll do here in just a minute. Hey, Matt. All right, so there's the answer. Object moving to the left, negative velocity, its speed is decreasing, it's slowing down, so the acceleration has got to be positive. Three types of motion graphs that are very common. The first is a position versus time graph. So on your vertical axis, you'll have position measured in meters. On the horizontal axis, you'll have time. Actually, all three of these graphs will have time as the horizontal axis. And anytime you have a graph, and this is not true just for kinematics, but for every graph that you see, all year long, there are a couple of things that you need to ask yourself that might be significant. The first thing is the slope. Does the slope mean anything? And the second is the area underneath the graph. So when you have a position versus time graph, everybody knows how to calculate the slope of a line, the rise over the run. Just ask yourself, well, what is the rise? What is the vertical axis? And what are the units for that? Well, position versus time, the vertical axis units are meters. And the run, the horizontal axis, is seconds. And so if you look at meters over seconds, meters per second, that sounds an awful lot like velocity, and that's exactly what it is. So if you have a position versus time graph, all you have to do is look at the slope, and you can use the term slope and velocity interchangeably. If you have a positive slope, you've got a positive velocity. You've got a negative slope, negative velocity. If you have a zero slope, you have a zero velocity. So looking at this position time graph right here, for segment A, that's a positive slope, a constant positive slope. So that means you have a constant positive velocity. If you wanted to find what the velocity during segment A was, just calculate the slope. Looks like it has a rise of 30 meters and a run of 3 seconds. So that would be 10 meters per second would be your velocity during A. During B, the slope is 0. The object's not moving. It's sitting there at 30 meters and it sits at 30 meters for from 3 seconds to 6 seconds. And then during segment C, notice you have a negative slope. So that means you have a negative velocity. The object is moving backwards, moving back to where it passes through where it started, position 0 at 8 seconds, and then it continues traveling in the negative direction from there. So the biggest thing about any of these motion graphs is once you determine what the slope is, you can, for example, in this graph, slope is velocity. You can use the terms interchangeably and answer some questions very quickly with a great deal of certainty in the accuracy of your answers. If you have a position versus time graph that looks something like this, notice that it's not a straight line graph, it's a curve. And so the slope at any given point in time is going to be different than for other parts of the graph. So this would be a graph with a changing slope. So it would have a changing velocity. And if your velocity is changing, that means that you're accelerating. So you can tell that it does have an acceleration because you have a curve, and you can actually get an idea as to the sign of the acceleration by looking at the concavity, if it's concave up or concave down. Concave up, like this graph is, means you have a positive acceleration. So you can't really determine exactly a numeric value for the concavity or for the acceleration, but you can easily tell that, oh, positive, you have a concave up, so that's a positive acceleration. Between points A and D, notice that from A to D, if you draw a slope to the tangent line at each of those points, it's a positive slope. But you get up to point D and the slope at point D is 0. So if I have a positive slope, I have a positive velocity, but the slope is approaching 0, that means the velocity is approaching 0. So from A to D, notice that's concave down, so that would be negative acceleration, and a positive velocity and a negative acceleration means the object is slowing down. So between A and D, it goes from a positive velocity to a 0 velocity. Here are your rules for concavity. Concave up, any of those graphs in the top portion of the slide are concave up. I was told at some point that if the graph is smiling, I think Ms. Dimmler, that was you that brought that up last time, wasn't it? If it's smiling, it's happy, it's positive. So that's a positive acceleration. The graphs along the bottom, they're concave down, they're frowning, they're not happy, they're negative, that's a negative acceleration. So you can, in fact, tell the acceleration sign, whether it be positive or negative, from a position versus time graph.
Yeah, my students like that little trick. It's totally not scientific, but it helps them remember that on a position time graph, if you see any part of a frowny face, that means it's a negative acceleration, and any part of a smiling face, it's a positive acceleration. So just a shortcut.
I mentioned, thank you. I mentioned a slide or two back that the slope of a curved line doesn't make a whole lot of sense, but you can draw a tangent line, which is what's shown in this slide, and then determine the slope of a tangent line. So that would be the instantaneous velocity at that particular point in time. Obviously, if you go forward or backward in time, that tangent line is going to be drawn differently. It would have a different slope, Therefore, you would have a different velocity. Mostly when you get position versus time graphs, they're going to be of the straight line variety with a constant slope. So there's an example of positive tangent lines. So you have positive velocity and it's concave up, it's smiling. So you have positive acceleration, it is speeding up. Notice that we went from position and displacement measured in meters, velocity measured in meters per second, and acceleration is meters per second per second. How many meters per second is your velocity changing every second, which is typically written as meters per second squared. But meters per second is a little bit more descriptive for acceleration and what's actually happening. It's the rate of change of your acceleration. So in which direction, look at the 4 possibilities down at the bottom. It says, in which direction are each of the objects below moving, and what is happening to the speed of each object? So first, when you see positive velocity, positive acceleration, positive velocity, it's moving to the right or up in the positive direction, and with a positive acceleration, it is speeding up. Positive velocity, negative acceleration, signs are opposite, it's slowing down. The third one from the top, negative, negative, it is speeding up. And the last combination, negative velocity, positive acceleration, again, it is slowing down. The type of kinematic graph that you're most likely to see is going to be a velocity versus time graph. And when I draw my position graphs, I start with the position versus time graph. I draw it at the top of the page. And then right below it, I draw a velocity versus time graph. And then below that, I draw an acceleration versus time graph. So the vertical units go from meters to meters per second to meters per second squared. If you have a velocity time graph, the slope of the graph is your acceleration. So whenever you look at the slope of a velocity time graph like this one, slope, as always, is the rise over the run. If you look at the units, that's a meter per second is your rise, divided by seconds becomes meters per second squared. And so you can use the terms slope and acceleration interchangeably on this graph. So from 0 to 3 seconds, that has a positive slope. That means there is a positive acceleration. From 3 to 6 seconds, 0 slope, that means 0 acceleration. A common mistake, and something I tell my students all the time, is before you start answering questions for a graph, make sure you understand what type of graph it is that you're looking at. And if I go back a few slides to the position versus time graph, in this graph, notice during segment B, this object is standing still. It is stationary. It's sitting there at 30 meters, and during that segment, it does not move. It has a 0 slope, therefore it has a 0 velocity. Meanwhile, if we go down, look at this graph, from 3 to 6 seconds, it's a 0 slope, absolutely. 0 slope means 0 acceleration, but this object is moving. It's moving at 16 meters per second for that entire time. It's moving at a constant velocity. So it's very easy to take a look at a graph like this and go, oh, from 3 to 6 seconds, it's not moving. Well, it is moving. It's moving 16 meters per second. So understand what type of graph it is that you're looking at before you start applying the slope and area rules. So the question here is, what is the acceleration of the object between 6 and 8 seconds? Well, all you got to do is find the slope of that line between 6 and 8 seconds. The rise is -8, the run is 2. And so the acceleration is going to be -4 meters per second squared. So The other thing, actually, let me give you an opportunity to answer these questions. Question 2. Which of the following represents an object having 0 acceleration? And notice that they're not all the same type of graph. That goes to what I was just referring to a minute ago. Graph A is a position versus time graph. B, C, and D are velocity versus time graphs. So see a combination of answers. Most are answering B. A few answers C. B says only graph B. Graph B absolutely is 0 acceleration because you have a velocity time graph. It has a 0 slope, 0 acceleration. Graph A also depicts 0 acceleration because notice graph A is a position versus time graph. The vertical axis is X, your position, and it's not smiling and it's not frowning. It's not concave up or concave down. Graph A has a constant slope, therefore it has a constant velocity. So actually graph A and B both indicate 0 acceleration. So this just kind of underscores the the common mistake that I see students make all the time. When you're interpreting a graph, make sure you understand what type of graph it is that you're interpreting before you get there.
I like to tell my students to, when there's a graph on the AP exam or a graph on a unit test or a graph that you're reading anywhere, actually physically circle the axes labels. So to make yourself aware of what kind of graph you're reading, whether it's a position time graph, velocity time graph, or acceleration time graph. And you need to really ask yourself, for the given question, should I just read the graph? Should I take the slope, or should I take the area of the graph? And those are the 3 questions you ask yourself after you read the question and you circle your axes labels. So just some pro tips there on how to handle kinematic graphs.
Exactly. And the area quite often is meaningful. On a velocity graph, it is. We haven't gotten there quite yet. We'll touch on that here in just a second. For the position versus time graph, the area means nothing. Because if you look at the units, to find the area under a position versus time graph, you're going to multiply the vertical axis, which is meters, by the horizontal axis, which is seconds, and you're going to end up with a meter second. And a meter second is not something that has any meaning, at least not in an AP physics class. Might mean something to somebody somewhere, but definitely not to us. We'll get into the area of a velocity time graph here in just a minute. Let's look at question 3 here. And we have a velocity time graph. And it says over the 9-second interval, we can say the speed of the particle only increases, only decreases, increases, then decreases, or decreases and then increases. Or I think the last option down there is remains constant. We got 3 answers vying for top billing. Looks like, well, now we're A and D running neck and neck. The correct answer is actually D on this one. It does have a constant positive slope, so it has a constant positive acceleration. But looking at a graph like this is where, one of the things I tell my students, and I remember having a long discussion with our calculus teacher a few years ago, that once I explained it in terms of a velocity time graph, yeah, I finally saw, the light come on. If you're slowing down, your velocity is approaching zero. That's, that's easy for people to get their heads wrapped around. So notice that this velocity starts down at what, -2.5 meters per second, but it's approaching zero. There are two ways you can approach zero: from below or from above. And so if you're approaching zero from below, that means you have a negative velocity, but that's clearly a positive slope on this line. So negative velocity, positive slope, you're approaching zero from below. But once your velocity is zero, slope doesn't change. Now you move into the territory of positive velocity. And if you're speeding up, your velocity is getting farther and farther away from zero. So this would be a constant acceleration. That's easy to see because you have a constant slope, constant positive acceleration because you have a constant positive slope. But for the first 3.5 seconds, the object is slowing down, the speed is decreasing, and then after that, it's increasing. I think you can convince yourself that if you had a positive velocity graph above the axis that was approaching zero from above, that would be a negative slope, positive velocity, negative slope. Notice the signs are opposite and it's slowing down. But then if it crosses the axis, you'd be negative velocity, negative acceleration, and it would speed up. So on a velocity time graph, just ask yourself, is the graph approaching zero? If it is, it's slowing down. If it is getting farther away from zero, it's speeding up. So the answer on that one is D. It decreases until it hits zero, and then it's increasing beyond that. The other thing that you can easily get from a velocity time graph is the displacement of an object. And the displacement of an object you can get graphically by calculating the area under the graph, or the area between the graph and the horizontal axis. So question 4 involves 3 different segments. They're labeled there: segment 1, segment 2, and segment 3. And it asks you to rank the displacement for the 3 segments of the object's motion. So if you get a graph like this in a question, you could, dust off your kinematic formulas and calculate the slope. That's going to be the acceleration, look at the initial velocity, the final velocity, the time, and calculate the delta x. But if you do that, you're doing way more work than is necessary. So on a question like 4, all you need to do is visually look at and compare the area under the graph for each section. You can count the number of squares. You can break them into triangles and rectangles and do it that way, whatever way works best. But basically, if you're wanting to rank the displacement from greatest to least, look at the 3 segments and see which has the greatest area and which doesn't. And that's something that you can visually determine most of the time. And everybody answered A. 3 is greater than 2, greater than 1. That is exactly correct. So it's find the area under the curve for each section: 4 meters, 5 meters, 6 meters for segments 1, 2, and 3. You don't even have to calculate the area. You can just visually inspect it and see how they differ. All right, so next question. This is where you get to draw a little bit. Circle the graphs that show constant positive acceleration. Draw a square around the graph which shows 0 acceleration, and draw a triangle around the graphs which show a changing acceleration. So I'll give you a second to do a little bit of artwork. getting a lot of participation in Pear Deck tonight, so I appreciate that. I know the study session at 7 in the evening is not always everyone's idea of a good time. All right, so let's discuss these. Constant positive acceleration. If you have a constant acceleration, these are all acceleration versus time graphs. So a constant acceleration is just going to be graph 1. That horizontal line, the acceleration is not changing. Zero acceleration, well, that's graph 5 down there at the bottom right. The acceleration is 0 and never changes. And a changing acceleration, the triangle, are going to be graphs 2, 3, and 4. For the most part, you will not see problems involving a changing acceleration in terms of a kinematics problem. The only time I would anticipate you seeing a changing acceleration would be for springs and pendulums, simple harmonic motion. But for the most part, with AP Physics 1, you'll be dealing with a constant acceleration or zero acceleration. All right, the kinematic equations. These are copied and pasted exactly as they appear on your AP Physics 1 formula sheet, the one that you'll get when you take the exam in May. At the beginning of the year, every year, I print copies of the AP formula sheet, and I give each student a copy, and I have them use them on every test, every quiz, every assignment, so that they get accustomed to, seeing the formulas, know what's there. I let them write any kind of notes or auxiliary formulas or whatever they want on the sheet. And I also show them a few changes that I would suggest that they make. For these formulas, notice like the first one, Vx is equal to Vx naught plus AXT. All that little X subscript means is that that's the X, or the horizontal dimension. First thing I tell my students is get rid of the X. These formulas work perfectly well in the vertical dimension as well, in the Y dimension. So that X is completely not necessary. So I would write this as V equals V naught plus AT. Final velocity is equal to initial velocity plus acceleration times time. So going down to the middle one, X equals X naught plus Vx naught T plus 1/2 AXT squared. Do the same thing, get rid of the little X subscripts. And then I take it a step further. I subtract X naught from both sides. And so on the left-hand side, I just have X minus X naught, and I write it as delta X. A problem seldom will give you, the initial position of the object was 12 meters and the final position was 18 meters. What you're really interested in is what is the displacement, which would be 6 meters, the final minus the initial. So I write the second one as delta X equals V naught T plus 1/2 AT squared. It's just a whole lot more useful and manageable at that point. And then for the third one, take off the X subscripts, and then notice there in parentheses, you have X minus X naught. I just replace that with delta X. So V squared equals V naught squared plus 2A delta X.
That's great advice, Paul. I'm stealing that because my students get confused by the sub X's all the time.
I never have them write them. I really wish that they weren't there because they don't add value, in my opinion.
I agree.
We'll do two-dimensional motion coming up here shortly, and these formulas work perfectly well in the Y direction as well, in the vertical direction. So one thing to notice is that there are 5 kinematic variables. You have initial velocity and final velocity, acceleration, time, and delta X. Each of these formulas has 4 of those variables. Acceleration shows up in all of them, but the first formula has no delta X. The second formula has no final velocity, and then the third we call the timeless equation, it has no time. So when you're working a kinematic problem and identifying variables, it helps to list them all out, and that will help steer you in the direction of one of these formulas. So using the kinematic formulas, a lot of it is going to be reading for information. And just when you're reading, an object starts from rest. Well, that doesn't tell you that the initial velocity is 0, but that's one of those key words that you need to pick up on. Or an object comes to rest. That means its final velocity is 0, which is very useful information, a lot of times not given to you directly. But once you identify all of your variables, figure out which of the kinematic equations is going to be useful to you, and then plug in what you know and solve for what you don't. Looking at there's a reference to a constant velocity formula. And if you have a constant velocity, basically your acceleration is 0. So going back real quick, if acceleration is 0, the first equation, final velocity equals initial velocity. Well, that's true, but that's not real useful. The second equation would be delta x is equal to v naught t. Because if acceleration is 0, that 1/2 at squared goes away. And that is the constant velocity. Basically, it's your displacement is equal to your velocity times time. If I'm traveling at 5 meters per second for 3 seconds, my delta x, my displacement, would be 15 meters. So that's what's referred to as the constant velocity. And that comes into play definitely when you do two-dimensional motion. Question 6 says a racquetball strikes a wall with a speed of 30 meters per second to the right, rebounds in the opposite direction with a speed of 26 meters per second. The ball is in contact with the wall for 20 milliseconds. That would be 0.02 seconds. What is the average acceleration of the ball during the collision with the wall? So notice that there's no mention of delta x, of the displacement. So that would lead you towards kinematic number 1, v is equal to v naught plus at. Or another way of writing that would be acceleration is equal to the change in velocity over time, which by definition, that is the definition of acceleration, change in velocity over time. There's one little bit of a gotcha in this problem. Give you a second to do some calculations. See, one answer so far. So I have a C and a B, or excuse me, an E and a couple of B's. Someone briefly chose C and decided against it. C is actually the correct answer, negative 2,800. Here's the thing to be aware of with this problem, and it might help if you drew a picture. It says a racquetball strikes a ball with a speed of 30 meters per second to the right. So it's traveling to the right. So its initial velocity would be 30 meters per second. It rebounds in the opposite direction with 26 meters per second. Well, that's going to be a negative 26 meters per second. So your initial velocity is positive, your final velocity is negative, and your delta V, your change in velocity, is going to be final minus initials. So it ends up being negative 56 meters per second divided by the 20 milliseconds. So the correct answer is actually negative 2,800. The problem didn't tell you that the velocity was negative, but you had to conclude that based on the context of the problem. So that's an example of where problem or a picture might be very helpful, useful to you. All right, gravity problems. Very common type of problem. If I toss something up in the air, the instant it leaves my hand, it is accelerating due to gravity downward. On the way up, it is accelerating downward. At the very apex, it is accelerating downward. And on the way down, it is accelerating downward. Gravity never stops pulling down towards the center of the earth. This shows G as being 9.81 meters per second squared. We always, or AP always allows you to use 10 meters per second squared or -10 because it's in the downward direction. And that makes the mental math just a whole lot easier. A whole lot easier to multiply and divide by 10 than it is by 9.8. So if you have a position versus time graph, say you're on the top of a building and you drop something. Notice that the position versus time graph, the initial slope is 0 or very small because it starts from rest, but then the slope of the tangent line gets greater and greater and greater, and it's negative and getting more and more negative. Notice that this is a frowny graph, negative acceleration, which makes sense because it's accelerating due to gravity, and have a negative slope. So negative velocity, negative acceleration, it's speeding up. Meanwhile, the graph on the right-hand side, the velocity versus time graph, represents the exact same motion. The initial velocity before I dropped the object, before I dropped the rock from the top of the building, was 0, and then it's speeding up on the way down, so it's moving faster and faster in the negative direction, and the slope of this line is going to be negative 9.8 meters per second squared, or negative 10 meters per second squared, if you will, for AP purposes. And it's a constant negative slope, meaning you have a constant negative acceleration. So both of these graphs represent the exact same motion. I'm going to skip question 7. It's just a little bit longer and more tedious than we have in the next 15 or so minutes. With projectile motion, basically this would be, you kick a football and it travels both horizontally as well as vertically. Or I throw a baseball, or I throw a football, or something along the line. I shoot an arrow, fire a gun, whatever, fire a cannon, whatever the scenario happens to be. It's moving in 2 dimensions. It's moving up and down vertically, and it's also moving left and right. If you think about the free body diagram, and I know I'm going away from kinematics, but I tell my students most every problem in the universe could probably benefit by starting with a free body diagram. Once an object leaves your hand or leaves your foot, it's flying through the air. The free body diagram for that object is very simple. You have one arrow pointing straight down towards the center of the earth, and that is the gravitational force. And if the force is pulling it down, that means it's accelerating down. So an object in projectile motion is accelerating vertically, and it's always accelerating down. Horizontally, it's moving at a constant velocity. So horizontally, you've got that delta x is equal to v naught t, and there is no acceleration in the horizontal direction. Usually you'll see a caveat or a clarification that air resistance is negligible. That just simplifies the math a little bit. When it comes to projectile motion, especially if it's on a free response question, I can guarantee you that there's going to be a rubric point or two that says something along the lines of student recognizes that they can separate the vertical motion from the horizontal motion. So when I have my students working projectile motion problems, I have them create two different tables or two different lists, one for the vertical motion, one for the horizontal. Vertically, you've got your 5 kinematic variables: initial velocity, final velocity, acceleration, delta x, and time. Horizontally, you've got delta x, your velocity, and time, because horizontally there is no acceleration. So horizontally it becomes very, very straightforward. You may get a question at some point that talks about maximum range. As it turns out, 45-degree angle is going to give you the maximum horizontal range. Angle any greater than 45 degrees will travel higher, certainly, but not as far horizontally. An angle less than 45 degrees isn't going to spend as much time in the air. It's not going to go as high, nor will it go as far. And that last bullet point is, I haven't seen this really as a key idea, but for example, something launched at 80 degrees and 10 degrees will have the same horizontal range. 70 degrees and 20 degrees will have the same horizontal range, and so on and so forth. When you're working projectile motion problems, the vertical problem can be treated independently of the horizontal problem. And what's a very common technique is you might have to solve for a variable, and usually that variable is time, because time starts when the projectile motion starts and it stops when the object hits the ground. Or if you're wanting to measure the maximum height, it stops when it reaches its maximum height. So a very common technique is you may have enough information to solve for time on the horizontal side, and then you move that time value over to the vertical side and solve for some vertical question that's being asked. Or it's possible you may be able to solve for time using the vertical motion and then move over to the horizontal motion. But with vertical motion, it is always accelerating, and the acceleration is always negative 10 meters per second squared. So notice here on the horizontal side, you've got x final and x initial, also known as delta x, is equal to v naught t. So horizontally, no acceleration. Vertically, you've got all of the kinematic options available to you, because you could have any combination of those 5 vertical variables. One thing that I have seen this type of question before, the way I describe it to my students is, well, what happens on the way up happens in reverse on the way down. So this diagram clearly shows that. Notice that first of all, the x velocity, that arrow to the right on each of these dots, it never changes length. So that's another, a visual confirmation that the horizontal velocity is constant. But meanwhile, notice the vertical velocity on the way up, that arrow is getting smaller and smaller until at the apex, the vertical velocity is 0, because that's where the velocity goes from positive to negative. And to go from a positive number to a negative number, you have to pass through 0. But then notice on the way down, those vertical velocity vectors, they have the same length as the corresponding vector on the ascent, but they're just pointing downward. So the final vertical velocity is going to be exactly the negative of the initial vertical velocity. So sometimes it's useful to look at just the first half of the flight or just the second half of the flight. Another common mistake I see students make all the time is I'll ask, well, what's the acceleration at the apex? And they want to say 0. And so I'll say, so gravity ceased to exist at the apex. No, it still exists. Right. It never stopped accelerating. The velocity is zero, but don't confuse velocity and acceleration. These next couple of questions, I'll just, we're running a little bit short on time, so I'll just kind of talk through them. Ethan throws a 5-kilogram ball horizontally from the edge of a 90-meter tall cliff with an initial velocity of 40 meters per second to the right. What range does the ball cover during its trajectory? First of all, there's clearly a distractor here. In this entire unit, we have not talked about mass. Mass doesn't factor into kinematics. It will certainly in later units in the year. But if I drop a paper clip and a baseball, they're both going to accelerate at 10 meters per second squared. Obviously, air resistance at some point comes into play, but that's not something that that we have to take into account. So the 5-kilogram ball is a distractor. 90-meter tall cliff, well, that's your vertical delta X. So on the vertical side, you would have a 90 meters for your delta X. Initial velocity of 40 meters per second to the right, well, that's a horizontal velocity. And what you're looking for is what range, that's your horizontal range. So it doesn't look like you have just a whole lot of information here, but you know the initial vertical velocity is 0. If I toss the ball horizontally and at the same time drop one from the same height, they're both going to hit the ground at the same time. Because once they leave my hand, they're both accelerating downward at 10 meters per second squared. So in a problem like this, you're looking for your horizontal range delta X, you have the velocity, you need the time. So if you go over to the vertical side, well, I know the initial velocity, vertical velocity is 0, acceleration negative 10 meters per second squared. The delta X, 90 meters would be negative 90 meters if it's traveling downward. And so you could solve for time vertically and then use that value to solve for your horizontal range. So that's what this is describing here. Use the equation delta X is equal to V naught T plus 1/2 AT squared. Well, your initial vertical velocity is 0. So that's where you get the negative 90 meters is equal to 1/2 times negative 10 times T squared. Solve that for T, you get 4.24 seconds. And then you use that time over on the horizontal side. But it's very important to keep your horizontal and your vertical variables separated so that you know which side you have enough information to work on. Question 9, I'll let you answer this one. It's more of a conceptual question. You do have to do a little bit of mental math, but you don't really have to use a calculator for anything. It's the same scenario just described. It says, what are the vertical and horizontal components of the ball's velocity after 2 seconds? And I'll give you a second to enter your answers. Like most of you are answering C. C is correct. That horizontal velocity, that 40 meters per second, that never changes. So you know it has to be A, B, or C. Vertically, the acceleration is negative 10 meters per second. So after 2 seconds, it's going to be traveling 20 meters per second in the negative direction or downward. So C would be your answer there. So there's the explanation for number 9. question 10, one thing I want to point out about 10, and we'll move on to the free response question, is if you have an arrow or something that's fired at an angle, so 40-degree angle above the horizontal and to the right, how long does it take the arrow to return to its original launch height? For a question like this, the first thing that you do is, if you have a velocity and an angle, you have to break that velocity into its vertical component and its horizontal component. And the stupid little memory jogger that I tell my students, but they never forget it, is there's a World War I recruiting poster, and it's Uncle Sam. He's pointing, out of a poster, and he says, "I want you." And I say, "What does he want you to do?" And they'll say, "Join the army." And I'll say, "Yes, he wants you to sign up for the army." So if you have that 60 meters per second and an angle, 60 meters per second times the sine of 40 degrees gives you the vertical component. And by process of elimination, 60 meters per second times the cosine of 40 degrees gives you the horizontal component of the velocity. So you immediately take that 60 meters per second and break it into how much of it is vertical and how much of it is horizontal. So it's simple vector resolution. The trig works every time. So the question then becomes, well, I have my vertical and my horizontal velocities. What else do I know? Well, you know your acceleration vertically, -10 meters per second squared. And usually on a problem like this, well, you've got a couple of options. Vertically, you could say, well, how much time does it take to reach its apex? Because at its apex, its final velocity is 0. And that helps simplify some of the kinematics. And if I figure out how much time it took to reach its maximum height, I can just double it, and that's how much time it took to come back down to the ground. The other option is, well, if I know the initial vertical velocity is positive, when it hits the ground, the final velocity is just going to be the negative of that. Either way, perfectly valid. Mentioned earlier, sometimes it's easier to look at just the first half of the flight or the second half of the flight and just recognize that it's symmetrical in terms of what happens on the way up happens in reverse on the way down and takes the same amount of time. It's a couple of minutes after 8. I want to touch real briefly on one of the free response questions. It's not uncommon that you'll be asked to derive an equation in terms of some values. So using part A, you can see a dart gun is being fired a distance d away from a target. And as it's fired horizontally, it's going to drop some vertical distance h. And the question here says, derive an equation for t, which would be the time in terms of h and g. So when you're deriving an equation, if you're not sure where to start with something that you know. Start with some formula from the formula sheet. And in this case, it's kinematic number 2. Delta x is equal to v naught t plus 1/2 at squared, or delta y they use in this case because it's the vertical dimension. As I mentioned earlier, the kinematics work perfectly fine in either dimension. And then start substituting in what you know. So if we look at the previous, h is the distance from the horizontal axis to how far that arrow falls. And so they replace delta y with -h. Vertically, the initial velocity is 0, so that v naught t term goes away. And that's equal to 1/2 gt squared. And just rearrange that, solve for t. So the time would be the square root of 2h over g. So if you're not sure where to start with the deriving equation, start with something you know to be true, and then start substituting in variables. And what I tell my students all the time, when you think you're done, go back and look at the original question and make sure that you've answered the question. It seems obvious, but here it says derive an equation for t in terms of h and g. So if you've got something other than h or g, the 2 is fine, the square root sign is fine. But if you've got, some theta or some velocity or something over there on the right that the problem doesn't allow, you need to go back and refine what you're doing. I think I'll wrap it up at this point. There was a little bit more to this question and another free response question, but basically, when it comes to projectile motion, two-dimensional motion, just separate the vertical from the horizontal. That is, 90% of the battle, and recognize that you can treat each one of those as a separate problem, with time being the variable that ties the two together. So I appreciate everybody's time. Ms. Demler, any questions from the chat that anyone has posted or wants clarification on anything?
No one has sent a question in the chat, but since we still have a few minutes left, I just want to say, if you have questions now, please just unmute yourself and ask. I also want to say that I'm posting 2 things in the chat. One is a student survey, and I would like you to fill that out. The other is student notes that are associated with this session. So you'll see 2 different links in the chat. Again, one for the survey and one for the notes. But since we have a few minutes, now's the time. Ask questions if you have them about the content of kinematics. Any questions? I wrote a few notes down while you were talking, Paul, just notes like maybe we should mention this. And one of the things my students struggle with is understanding when they're reading kinematic stacks of graphs, understanding the difference between identifying a slope as positive and identifying a slope as increasing in steepness. Those are 2 different things. So slopes of graphs, whether it's a position time graph or velocity time graph, usually a position time graph, whether a slope is positive or negative is different than whether a slope is increasing in steepness or decreasing in steepness. Those are 2 different properties on that position time graph, and they tell you 2 different things. So I just want you to be aware of that. If a slope is positive on a position time graph, that means the object is moving in the positive direction. If a slope is negative on a position time graph, that means the object is moving in the negative direction. It has nothing to do with whether an object is speeding up or slowing down. What has to do with whether an object is speeding up or slowing down is that concavity, or whether the steepness is increasing or the steepness is decreasing. The other thing I wanted to mention was, I'm just thinking about what my students struggle with, and we constantly have to come back to the difference between a time interval and a moment in time. And you could think of a moment in time as like a selfie. If you take a selfie, you have captured a moment in time, but if you take a video, that's a time interval. And when you're analyzing physical situations, being aware of analyzing a physical situation at one moment in time, and then a second moment in time, and then understanding when you're analyzing an entire time interval. Those were the 2 notes I had. Thanks everybody for coming out to the session, and we wish you luck throughout the year, and hopefully we'll see you again at another session.
Okay, actually, as you mentioned that, there's one last thought that is not mentioned in the deck, but it bears mentioning. The slope, as we said, of a position time graph gives you velocity. Slope of a velocity time graph gives you acceleration. Slope of an acceleration time graph gives you nothing that you care about. So sometimes the slope means something, sometimes it doesn't. But moving in the opposite direction, if you find the area under an acceleration time graph, you're multiplying an acceleration times a time, and that gives you the change in velocity. So the area under an acceleration time graph is useful, as is the area under a velocity time graph. So out of those 3 graphs, the velocity graph, the slope, and the area are both meaningful.